This video contains the solutions to the line integrals practice problems. For this first one, we have to compute the line integral over c of f ds, where c is the upper half unit circle parameterized by r of s equals cosine of s sine of s for s between 0 and pi, and f of xy equals x plus y. So there's a lot of information being given to you here, but the main thing to keep in mind is that the curve that we're talking about is this unit circle, and since it's parameterized with x equaling cosine and y equaling sine, that's our standard parameterization, so we know that's going to be a counterclockwise parameterization. And so what we're really doing is integrating this function from this point 1 comma 0 to this point negative 1 comma 0. So the first thing we need to do is figure out whether this curve is parameterized by arc length. And the way that we do that is by figuring out the magnitude of r prime of s. In other words, figuring out the speed of this parameterization. So since r of s is cosine s sine s, r prime of s is negative sine of s cosine of s. What's the magnitude of that vector? Well, it's the square root of negative sine of s squared plus the cosine of s squared. That's sine squared plus cosine squared. And we know that that's 1, and the square root of 1 is 1. So that means that this curve is, in fact, parameterized by arc length. So we can simply integrate from the starting value of s to the ending value of x, from 0 to pi, of our function x plus y, but now we're going to take the x component of our parameterization and our y component of our parameterization and substitute that into our expression. So what we really get is, instead of x plus y, we get cosine s plus sine s. And then we can just integrate that with respect to s, since our curve is parameterized by arc length. So when we take our antiderivative of cosine is sine, so we get sine of s, minus the antiderivative of sine. The antiderivative of sine is negative cosine of s. Plug in pi, plug in 0, and subtract. So we get sine of pi minus cosine pi, minus the quantity sine of 0 minus cosine 0. That's minus minus 1 minus minus 1, which is 2. We have another line integral here. This time the curve is a line segment given by this parameterization, and our function is x squared plus y squared. So again, we need to figure out whether our curve is parameterized by arc length. So we need to look at r prime of t, which is going to be the vector 6, comma 8. And we can already probably see that the magnitude of r prime of t is not going to be 1. In fact, it's going to be the square root of 6 squared plus 8 squared. That's the square root of 100, which is 10. But the good news is that when we want to perform a line integral, we can still set up our integral in the normal way. We just have to multiply by that speed factor. So our function is x squared plus y squared, but we need to substitute in the parameterization. So instead of x, we put in negative 2 plus 6t squared, and instead of y squared, we have 5 plus 8t squared. And then we multiply by that speed factor, which is 10, and then we'll integrate that with respect to t. So we have some algebra to do. When we multiply out negative 2 plus 6t squared, we get 4 minus 24t plus 36t squared. And when we multiply out 5 plus 8t squared, we get 25 plus 80t, and then plus 64t squared. And that's still all multiplied by 10 dt. Collecting like terms, we have 29. Negative 24 plus 80 is 56. And then 36 plus 64 is 100. And then that's all still multiplied by 10. So we can take the factor of 10 out. Let's take our antiderivative. We get 29t. Plus 56 divided by 2 is 28t squared, and then 100 divided by 3, t cubed. When we plug in 1, we just get all those coefficients. When we plug in 0, we get 0. So this is just 10 times the quantity 29 plus 28 plus 100 over 3. And that works out to be 2710 divided by 3. Another line integral. This time they didn't give us a parameterization, so we're going to have to come up with our own parameterization. Now, we're parameterizing a line segment here, and if you recall, we have a standard way of parameterizing a line segment. So the line segment from a comma b to c comma d can be parameterized in this way. X equals t times c plus 1 minus t times a, and y equals t times d plus 1 minus t times b. When t is 0, this gives us x equals a and y equals b, and when t equals 1, this gives us x equals c and y equals d. So this gives us a linear function for x and y. So in this case, we're going from 0, 0 to 5, 12, and so that's going to give us the equation x equals 5t and y equals 12t. And as you can see, when t equals 0, we get 0, 0, and when t equals 1, we get 5, 12. So this is that parameterization of that line segment. So now we need to know what the r prime vector is. Our speed factor is going to be the magnitude of the derivative of 5t, 12t. So our r prime vector is the derivative of 5t, which is 5, comma, the derivative of 12t, which is 12. So our speed factor is the square root of 5 squared plus 12 squared. That works out to be 13. And so our line integral of c f ds, is going to be the integral from 0 to 1. Remember, our parameterization starts at 0 and ends at t equals 1. Of our function with our parameterization plugged in, so x squared plus y squared is going to be 5t squared plus 12t squared. That's using these equations down here, plugging them into our function f of xy equals x squared plus y squared, multiplied by that speed factor, and then dt. So what we end up with is the integral from 0 to 1, that's going to be 25t squared plus 144t squared, all multiplied by 13. That's going to give us, we can take the 13 out, that's going to give us 169 t squared dt. Take an antiderivative, we get 13 times 169 divided by 3, t cubed. Plug in 1, plug in 0, and subtract. And that's going to give us 2197 divided by 3. Another line integral here. Again, we're not given a parameterization, but we're told that we want the portion of the unit circle that lies in the first quadrant. So in this case, that's the curve that looks like this. Goes through the point 1, 0 and the point 0, 1. Since it's the unit circle, we can parameterize it in the normal way by letting r of t be cosine t, comma, sine t. This would be a counterclockwise parameterization, and if we want to start at 1, 0 and end at 0, 1, we want t to go between 0 and pi over 2. So we're just using our knowledge of polar coordinates and trigonometry here to get that parameterization. Now we know that this is a parameterization by arc length, but let's just make sure that we are checking this. So our speed, our velocity vector, our derivative is negative sine t, comma, cosine t. Our magnitude of our velocity vector, our speed number, is going to be the square root of the sum of the squares of those components. And that is, in fact, going to work out to be 1. So our integral is an integral from 0 to pi over 2. Our function is 2xy, so that's going to be 2 times cosine t times sine t. Our speed factor is 1, and so we integrate with respect to t. Now we can do this integral with a quick substitution. U equals sine t, and then my du will equal cosine t, dt. I have a copy of cosine t and a dt. So my new integral, I can pull out the 2, I just get u du. And my new bounds, well, t started at 0, so u is going to start at the sine of 0, which is 0. And then t went up to pi over 2, and so u will go up to the sine of pi over 2, which is 1. So that's just calculating, plugging in the old bounds into my substitution function to get my new bounds. So antiderivative of u is going to give me 1/2 u squared. Plug in 1, plug in 0, and subtract, and so I just get 1. Finally, we have one more line integral. This time our curve is split into two pieces, a line segment from -1, 0 to 0, 1, and then another line segment from 0, 1 to 0, 3. So the way that we're going to do this is by realizing that our overall line integral of FDS is going to be the integral over the first half of that curve plus the integral over the second half of that curve. So we're going to do these two problems totally separately, and then our final answer is simply going to be the sum of the two answers that we get for those two curves. So let's start with the line segment from -1, 0 to 0, 1. Using the standard line segment parameterization that we talked about before, what we get is x equals t times the ending x value, 0, plus 1 minus t times the starting x value, negative 1. And that works out to just be t minus 1. Y is t times the ending y value, which is 1, plus 1 minus t times the starting y value, which is 0. So that just gives us t. So our parameterization is t minus 1, comma t. Is that parameterized by arc length? No, because r prime of t is the vector 1, 1, and so the magnitude of that vector is the square root of 2. Square root of 1 squared plus 1 squared, which works out to be the square root of 2. So our integral over this portion of our curve of f ds is going to be the integral from 0 to 1. Remember, when we parameterize these line segments, we always go from 0 to 1. Our function is 2x minus 3y, so that's going to be 2 times t minus 1 minus 3y, so minus 3 times t, times our speed factor, which is the square root of 2, and then we integrate that with respect to t. And when we work all that out, what we're going to get is negative 5 radical 2 over 2. So that's our first portion of our line integral. Now we're going to look at our second portion of our line integral. We're going to go from 0, 1 to 0, 3. Now what we could do is the same thing, to parameterize that line segment using the standard parameterization, but we can also make our lives a little bit easier by realizing that 0, 1 is this point here on my y-axis, and 0, 3 is this point here. And so I could parameterize this curve simply by letting r of t be 0, because the x is just going to stay 0 the whole time, and then t, and then I'll just let my t go from 1 to 3. So that's just going to be a parameterization that I can just visually see by letting my y value go from 0 to 3. Now if you didn't notice that, or if you don't like that, we can do it this way. We can do it using the standard parameterization. It's just going to be a slightly different formula, but the line integral should still work out to be the same value. This way is just a little bit easier. It also turns out that this parameterization is parameterized by arc length, because my velocity vector is the vector 0, 1, and my speed factor, the magnitude of that vector, is just going to be 1. So that means that my integral over c2 of my function f ds is going to be the integral from 1 to 3 of my formula, which is 2x minus 3y, so that's going to be 2 times 0 minus 3 times t, multiplied by my speed factor, integrate with respect to t. And when we work that out, what we end up with is negative 12. So the two portions of our line integral are negative 5 radical 2 over 2 and negative 12. So we add those two numbers together, and that would be the total value of our line integral over the entire curve.